one big number.
You guys, I've wanted to do this for a while, but I've wanted to do this for a while, but this is my first time. Okay. So, what is this?
That's a multiplication table.
Multiplication table.
From 1 to 10.
From 1 to 10. And what are some things that we noticed about this multiplication table?
Perfect squares.
Perfect squares, symmetry.
Perfect squares up to diagonal. If you add the diagonal from the top left to bottom right, you get triangular numbers.
You guys know a lot about this. Okay. What about the fact that some of these numbers happen in more than one place? So what about the fact that we have a 4 here, we have a 4 here, and a 4 here? Do we see that sort of thing happening anywhere else?
8, 8, 8, 8.
8, 8, 8. Okay, so 8, 8. You guys are seated well.
Oh, the 12s look kind of neat.
10, see this in
10.
9.
We said 9.
Oh, you something on the other one?
16.
Okay, let's sort of work with the ones that. So my question in looking at this multiplication table is it tells me that there are 3 ways to make 4. So 1 times 4 is 4, 2 times 2 is 4, and 4 times 1 is 4. So those are the only 3 ways in the whole entire universe to make 4, right?
No.
No.
Of integers.
Of integers. What are you talking about?
Whole numbers.
Whole numbers.
Whole numbers. What are you talking about?
Operation.
Operation.
I could have 8 minus 4 is 4.
Okay, well, we'll specifically looking at the multiplication.
Alright, but you didn't say that before.
No, I appreciate it.
Other ways to make 4. So yeah.
Negative 2 times
You're
negative
gonna take
2.
one stick over.
So that's why we said whole numbers.
Okay, so we're looking at whole numbers, but thinking specifically about 4, there are other positive numbers that you can multiply to get 4.
Fractions. Fractions.
It's like a half.
Rational numbers.
A half times 8. Half. How do I get a half on this table?
Yeah, squeeze in there.
Okay, squeeze it. Okay, so half.
No.
Is it here?
0
No.
and 1.
Ah, 8. So we can also make 4 here. Okay, that's interesting.
Ooh.
Is there anything 3 times anything?
Well, it seems like if you could draw a line from those 4s, you get something kind of different.
Oh, that's a really interesting idea. You want me to draw? Okay, so I draw a line through the 4s like this.
No.
Yeah, because you could do the same thing the other way, 8 times 1/2. So put another point over there that 8 and
About 3
1/2.
times 4 thirds.
Right
Looks like
here,
a-
yeah. If you do this line, you get this
Okay,
kind
can you come draw this line for me? Because I love squiggly lines, and I'm going to want to squiggle all over the board. Oh, sorry.
I'm not tall enough. Okay, looks like it kind of does this.
Yeah,
It's a great curve.
It's beautiful.
Oh.
Good job, Lisa.
And it ends there?
No, I bet we could just keep going and going and going and going.
Okay, okay.
Can you prove that?
So I'm going to put an arrow on the end just because I'm obsessed with like that. Okay, so we got 4s. Okay, that's the only thing that works like that then, just only 4s.
Yes.
No, they all work like that.
They all work like that. Can you show me another one that works like that?
Because it's just
Which
x
color?
times y equals. It is just cool seeing it
For 8.
with the multiplication table.
And they're right here. Is root 8.
Ah, roots. Ah, okay.
Nice.
And so why did you put the root there? Why was it? Why did your line? I mean, your line could have gone like this, or your line could have gone. Why did you put it there? Maybe I want you to sort of think about that when we get up to something like.
Because the perfect squares are on the y equals x line.
Right.
So
Okay, let's see. Good point.
I probably drew it too far to the right. So.
So what about this
Well,
36? So we got 36 here. 36 here. 36 here. How would a line through 36 work?
Same. Similarly to what we've
This
done.
is a curve.
Well, just because when you're looking at it.
But this one to me looks really straight, right? We just go straight through the 35,
For
through
now.
the 36, right?
So we extend the.
If you
extend
zoom
the-
out, would you zoom out? I think that
No,
board
because
is
if you go-
warped.
Just two fingers.
If you go down 3/2,
Two fingers.
you won't go down 3/2 again. So it's not on a line.
Okay, it's not on the line. We still need a curve.
Yeah.
Okay, so
Goodness.
where's between these two am I gonna go? Or am I gonna go over here or over here? What two numbers am I gonna go between?
Between 32 and 40.
Okay. We're gonna go really close to the 35. Really close to the 35, but still to the right. I just thought of this when I was trying to just where do you put the lines? You know, how do you get it all filled out? Okay. So these lines seem sort of arbitrary. Is there a way that I can make these lines straighten out? What do you think? Work on your graph papers. Think if there's a way that you can take and make. How would we make these lines straight?
Change your scale.
Change your scale. Change the scale of what?
Do I have to make them all straight at the same time?
I want them all straight at exactly the same time. I want one plot where, the slope, I still want a slope that goes this way. But I still want straight lines.
Change your arithmetic means to geometric means.
Can you show me what you mean with the picture, or talk to your neighbor, and what are we thinking? Is there any, I liked the scale idea. Change your scale. Change your scale of what? What number do we want to work with? Let's go for 4. Okay. So somewhere over here we have 4. Equal distance. 4. Not gonna work that well. Okay, I'm gonna make 4 closer. Sorry.
I like to.
And I want a straight line. That everywhere on the line, what does this line represent?
All the fours
All of the 4s. All the 4s what?
that you
No, it's a
achieve
quadratic.
by multiplying two numbers together.
X times Y equals.
So, everywhere, every XY pair on this line, what? XY equals what? As X times Y equals 4. Do we agree?
No.
What's the goal?
That's the goal.
Is that the line?
But
Well,
that's
I
what we
want a
want.
straight
We wanna
line,
do
and I want
something to make
everything on that
happen.
line to be such that X times
Oh,
Y
I think it was a
equals
curve.
4.
Sorry.
Right, it was a curve over here.
No,
right?
it looks like a curve over there, and I was like, why did you flip over the curve?
Oh,
Never mind. My eyes are tired.
It's
Just
just that
that
top arrow is kind of.
oh yeah, it is.
Okay.
Imagine this is a straight line, and that I can draw on a board.
Deflate the balloon.
So wait, can we take the axes and just like stretch them out like that?
Stretch them out like that. What do you mean by that?
Like, so basically, instead of thinking of it as multiplication, because we have like a coordinate grid with x and the y-axis.
Uh-huh.
If you were to take that x and the y-axis and take the ends of it and then pull them out towards each other so that they make a 45-degree line, then you're taking all the points within the plane and stretching it out so it's a semicircle.
Okay.
And then now all of these, the curves, the 1 over x curves, will now run parallel to that new axis, which is the xy axis together.
I think I almost got it, and that's an awesome idea, especially like I would love to visualize that sometime. But
Me too.
what I'd really like to do is definitely keep my X, Y perpendicular to each other.
think
Okay.
Well, we have the midpoint there. So
But I sort of want to stretch it. Midpoint. What are you
2
talking
times
about?
2 has to be
2 times 2 has to be on there. Oh man, okay.
The closer that you get to 0, the longer you should maybe stretch it. So you're doing like some proportional stretching.
So we think closer to 0, more stretching, proportional. Oh, I can't do
Maybe
proportional,
less
I can't spell
stretching.
while I'm lecturing, I'm sorry. But I know, we're gonna remember that we're thinking
Some kind of
proportional
proportional
stretching.
Well, zero
Yes.
times two has to be on there.
Need 2 times 2 and other sort of integers that we know about.
But that's also symmetric, so if the graph is symmetric, that has, wouldn't that be?
To be there. And 2 is symmetric. Ooh, okay. I really can't spell on the board. I have to get better at that. Okay. What do you mean by that? Can you come show me where you think a point is going to be?
Well, I would say right in the midpoint of the orange line, if the two axes are the same scale.
Okay. Same scale.
If they're the same scale, it's got to be the midpoint of that orange line. 'Cause otherwise it wouldn't make it. It's got to be
Here?
the midpoint, right? So it's got to be, 45 degrees. Yeah, it's got to be somewhere there.
2, 2. We got and this one is going to be.
Mark has comment.
Yes.
Yeah, that was basically what I said, because the geometric mean of 1 and 4 is 2. And the arithmetic mean is 2.5. So you're putting the geometric mean where the arithmetic mean normally is.
Okay. Now let's keep building after this. Okay. So with that, where can we draw our next line? What's our next one we want to do?
Well, the square root of 2 would be halfway between 1 and 2.
Okay.
Did we prove why those endpoints need to be 4, 1 and not infinity, comma 0?
Just because I defined them to be 4, 1, and 1,
She
4.
wants all the lines parallel. If you had infinity on there, they don't come together. They're all one off.
Well, I think there's like where 1.5, 8 go.
Right, yeah, that's my question. Like, where does 1.5, comma 8
Yeah,
go?
if that's 1, it's
Well, I want to end at 8, comma 1. But that's a great question. Well, I don't want to do 8, comma 1. I don't want to be over here. I want to. 1 is definitely going to be
This is the smallest.
the smallest that I want to deal with right now. Yeah. But we could deal with 1/2.
So the other one between 2 and 4
Sorry.
would be
You don't
2
have to
square
not
root
be
of 2.
included if you're videotaping. You can have.
So the midpoint between 2 and 4 would be 2 square root 2. Because, I mean, that's got to link. That's got to, okay.
Okay, but 2 square root 2. I know it's 2, and square root of 2 is
1.4.
what? I'm sorry.
1.4.
1.4.
So it's like 2.8.
So this is about what?
2.8.
So 3 isn't actually halfway between
No.
2 and 4. That's interesting. Okay, I'm gonna put that on our observation. Anything else? Where are we gonna put 3? What's another number that we can do right now?
So 3 times 4 points.
We got 2, we got 4, and we got 1.
8.
8? 8? Okay. I like lime green. I can do 8.
It's going to be outside.
So we're going to have 8.
You got the square root of 2 times square root of 2.
Yeah, we gotta go below 1.
Oh.
We gotta go off the top.
So we know if we have 2 and 4. I'm going to push this a little bit more than I would if you're students. Sorry. We can keep extending this. We know that this is 2 for sure. We know this is 4 for sure. So this is going to be
4, 2.
4, 2. And what line is that going to be on?
The 8 line.
8 line.
Or you can take the distance to 2 and the distance to 4 and add it on the x-axis. It works the same way.
Oh, really? That's interesting. The distance to 2.
Yeah, that's gonna be the
This is
2
4.
times 4 line right there.
Okay, so
That
That'll
should
work.
4, 2.
okay, so we need this line that goes. Okay, and every xy pair on this line is such that x times y equals what? we're getting straight lines. We had curved lines, we're getting straight lines. If I can draw straight. So where is 3 gonna go? Or what does this leave us to do? Or can we do anything else? Can we keep on adding?
We're gonna do the half.
Half?
Yeah, I mean, it's hard to get 3.
Has to go way up.
Can we graph in another quadrant?
What would, I'm not sure. What would that get us?
Well, because
Oh,
you kind
so
of have
there's a-
exponents. You have
Right,
negative
okay,
exponents,
so then you could do that.
but maybe not.
3D between 2 and 4.
I hadn't thought about it. It's possible. 3 would be between.
4 between 2 and 4, right?
Well, what's one thing that we know for sure about 3 times 3? 3
Nine.
times 3 is 9. So 3 times 3, and this is also square root of 2. Which is there. 9 is smaller than 8 or bigger than 8?
A little bit bigger than
So this is the thing, when I was doing this a lot today, when trying to draw these out, just to remember that 3 times 3 is definitely going to have to end up on this side of the green line. Do we all agree on that?
Yeah. Okay, so it's a little bit more than halfway between 2 and 4.
So 3, yeah, there's a little bit there. 3, I'm just eyeballing this.
Is there a way that we can place that exactly?
I don't know. What do you think?
Yeah, let's do it.
Well, it's 3 is halfway between 1 and 9. So if you can find 9 exactly, you can find 3 exactly.
But that's, you're going circular, because you need factors, right? You can't get 9 unless you have the factors of 9, which is 3.
It's not so easy to get 3 on that chart.
Is there a way to draw some kind of triangle with a hypotenuse and then like swing it down so that it hits the line?
I think that would be an excellent exercise to keep working on, and I think to develop this further with your students. But one of the things I really want to sort of focus on here is can we step back now? You guys had tons of observations about this multiplication table. Is this still a multiplication table, or is this changed? Is this something else now?
This looks like an exponential.
Power table.
If I'm seeing powers of 2s, each even space is another power of 2s. So I would expect that the next step beyond that, it would be 16, but the same amount of space.
So it's still a multiplication table just on a log scale.
Right.
So, what I have for you to get you started, we're using the one that hasn't been marked up. And I meant to cut them, but here are scissors. You need 2 of these.
Two scissors?
You need 2 rulers.
Two
One to
rulers, so cut 2 of the 3 out?
Okay, so we're looking at the ones that's not marked. We're going to mark up the ones that aren't marked. And we need 2 of the ones that aren't marked cut out so that we can slide them past each other.
Okay, so 2
Oh, I was thinking
strips.
something else, he does function.
2 of the 6.
I think this is different.
So we're only cutting ones that are not marked.
Ones that are not marked.
Not marked.
Brandy, this sounds really stupid, but is one of these 2 of these?
One is, this is
One
one
strip.
and that's one.
That's what I wanna know.
So there are 6 strips, there's 6 rulers on the one strip.
Keep passing the scissors where they all.
Right, no, there is.
Yeah.
I'll never look at thirds again the same way.
I remember I did this in kindergarten.
Yeah, they're 3 pieces.
where we were cutting things off of one page and gluing out to the spaces on the other page. And then the continuity markers from the file. Cut them into strips and then cut them out. So I remember.
And what I want you to do,
So
Lisa made an observation. What did you say that
you know what I mean?
the scale was on this?
I printed it out.
Power's a 2.
I remember the teacher wrote
So at each inch mark,
yes, cut it.
what I want you to do is label each of the inch marks with powers of 2. So our first power that we're going to deal with is 1. Or so the 0 power is 1. And then we have 2, 4, 8, 16, 17.
It's okay. That's all I can say. You never copy it too. You never copy it.
But you might
I
not
think I'm just, on both of them or just one?
On both of them. On both of them.
What did you say then?
We need to label each one of them with powers of 2 on the inch, the tick marks.
The bigger, longer technique.
On
On
the
the-
inch or centimeter?
Mine,
Just
yeah, I
think of
guess
it as the longer line.
the longer tick, the longer line.
You show that in the inch or centimeters. Yeah, but,
So,
what are they? They're Brandy meters.
They're Eric shoe meters.
They're what?
Eric shoe meters.
That's what he invented them.
Well, he gave me the PDF. So.
That's all it takes these days.
Should we be doing one above and one below like you did?
I have no idea. We will soon find out and put it in the lesson plan. So going back to observations, what numbers are on this scale?
All
every number
Every 0.
from 1 onward.
Oh,
From
yeah, except
1
for 0.
onward, right. So right now we're really dealing with numbers that are 1 and bigger.
Square bracket 1, comma.
Yes. Yes. Not curvy bracket. Square bracket. My students didn't get that. Okay. So are we all pretty close to that?
How far do you want us to go?
I only went up to 64, but if you can go as far as you like. Some of
Some
us are really working on our power to 2. Because what we're going to do now is I want you to line them up. And my question is, what happens when you shift the top one to the right? What direction is that? So you guys, that's right?
Yes.
To the top and to the right.
It's not the other
Shift
way.
it to the right.
How far?
Oh.
What
How
happens?
Wait.
far to the right?
How far to the right?
Oh.
Well, let's take the
And
top
measured
one.
by which scale?
No,
Good
then
question.
the 2 times the top number equals the bottom number.
So that's if you have 2 above what? What's below and what's above? So 1 on the top is above what on the bottom?
2.
On the bottom.
1 above is on below, 2 on the bottom. And then 2 times 2 is,
Oh, wow.
and 4 lines up above 8, so that means that 4 times 2 is 8. 16 times 2 is 32. And what happens if we shift it over 1 more? We shift and we put 1 above 4.
So 1 plus 4 is 4.
The same thing?
Times 4.
Times 4. Times 4.
It's almost like we're sliding our ruler.
It's like we're sliding a ruler.
They should call it that.
Wow, that's real fast.
We're gonna make a fortune.
like 100 years ago.
If I have 1 over 4, I multiply
So
by
why
4,
would this
that's
ever
8 by
be
4 is
useful?
32 by 4 is
No.
She's just saying. She's just saying.
Because I don't want to memorize my 200 times tables.
Okay.
So what if we would have gone all the way out here though, right? So we kept, somebody did.
Yeah.
Somebody did. We're all.
I
She
should
did.
have further than
Okay.
Well, if I wanted 512 divided by 64.
So I'm gonna take and put 1 above 128. So someone tell me, just off the top of your head, what 128 times 32 is.
4096.
496. How did you do that so fast?
4096 because it's under my 32.
It's under your 32. So is this a quick way to do multiplication, probably faster than some of us might do in our heads? Okay. So.
But it depends on having labeled the ruler ahead of time.
And long enough.
And long enough and far enough.
Yeah.
Well, is there a way that we could do it? We've been talking a little bit about scaling, right?
So this is.
So,
This is
We could do it.
could we do something like, what's the difference really between, we were talking on a different scale. What's the difference? Well, let's look at this one. What's the difference between 2 and 20? Is the 20 line going to go through sort of similar dots? I'm saying this wrong, aren't I?
Right.
Well, it won't be inches.
We're actually saying where do we place it? We place from
Okay, how about this? Point 2. Let's do that. Point 2. So what would be, using our scales, what is 1 times 0.2? What would we do to ourselves? So we know that.
What time's 0.5?
0.5's power to.
Okay, there we go. See, I told you first time doing this lesson. 1 times a half.
Oh.
So go the other way.
That works out. Let's slide it out.
Well, now where is my half?
Oh yeah. Half is
Just
off
put
the
the 2
scale.
over 1.
But what can you do?
Put the 2 over the 1.
Put the 2 over the 1, so shift the other side. What if we wanted to do 1 over 4?
2
4
fourths.
over the 1.
Put the 4 over the 1.
But the answer's not on there. Like.
So 4 over 1 means 16 divided by 4 is 4. 32 divided by 4 is 8.
Right,
But
there's
1
no
over
answer.
4. What's 1 over 4? In other words,
Oh.
you've created a divide by 4 machine
Right.
for dividing whole numbers by 4, but what about dividing 1 by 4?
Well, okay.
So
Good
then
point.
you shift.
That's a different scale that we don't have here.
Yeah, it goes off the left.
Is that why we have another bar?
Right, so let's sort of do that. And, yeah. Two directions. And I apologize, I wouldn't normally ask you this, but we can either explore slide rules or I have a different type of rule slide to explore. So let's just do slide rules, but this is the other thing that I thought about using. So these are slide charts that were inspired by slide rules. And basically what they are is the same idea as slide rules, but it does things like metric,
No, they're bad.
meter.
Slide rules are bad.
Slide rules are better. Okay. Okay. So these are just another resource though in terms of, I thought it would be great for your students' understanding and then they could make their own one of these. So that's another direction that you could take your lesson plan.
Maybe you could make us a PDF.
Yeah. Okay. So the adventure of this is that every single one of these slide rules is different.
Yeah.
This will be my first ever slide rule experience.
You
I actually held one.
How many
So,
people here
well-
use slide rules for real?
Did or do?
Did. Do, I'm not asking.
So it's quite possible that some of these don't actually slide. If that's the case, just ask me and I have more.
Oh, no, it does.
Some of them may have the nifty little thing to make it easier to actually read. Some of them may not.
Yeah, I'm gonna replace my battery protector.
Oops, it's missing the slide rule.
Oh,
You got nice box.
You got
Where'd
the
you get all these
surprise.
I spent today on eBay.
I'm really impressed with what you did.
In order to mark, you were able to find so many slide rules on eBay.
About Brandy or eBay?
Say
It
about
says
this,
they're all
no,
sold
the
out.
state of our society. Everyone's getting rid of their slide rules.
But on a positive note,
You're such attractive machines.
so these ones it's a very diverse set of them. And what I found in the process of pulling together this lesson plan is that there is such a thing as the International Slide Rule Museum in Colorado. And they have classroom sets of these that they will
Where
send
is it?
to you in Colorado.
Where?
Littleton, I believe.
Oh, that's supposed to be.
Oh.
You're going.
And they will send you a full, complete classroom set. I think they have like a set of rules, and I'm sure you have to do like a deposit, but you have to send them back a picture of your class using them. And this way, so you can borrow ours. Ours will be in the Bay Area, but then also if you want to, so that every single person is doing the exact same one. So the other part that we have, which I don't think that they will mail you.
That is so
Three
soft.
slide rule.
Can you show us how to work with them?
This is a lot.
So my question for you is, what do we notice?
The middle slide.
Hopefully your slide rule slides.
You have two sides.
Good so far.
We have two sides. Does everybody have two sides?
No.
What I want you to do for some of you, everyone should try this, is I want you to pull on your side, and I want you to see if the other side is different
On the back?
on the back. Because some of you may have a backing that you can actually pull yours out and switch sides and put back in.
Mine's all unit conversion.
Okay.
Mine has nothing. I had to change it over so that I could actually use it.
So those are the two sort of possibilities just to be aware of. So what are the sort of things, what do you see on the slide rule?
A lot of lines.
A lot of lines.
And letters on the far side.
Lots of
below.
numbers.
Changes
Lots
the
of
scale.
numbers.
Okay,
Are the lines all equally spaced?
So the scale changes.
All the little ticks.
The scales change. So that's why I did this activity in the beginning, because there is definitely different scales, but especially like when you're doing multiplication,
13 times.
the same sort of principle happens. So those of you that have multiple scales, what I want to see is, I want A, B, C, and D.
Okay. Right here on the left of those letters. I think that's what we're going
A,
Oh, yeah.
B, C, and D. Okay.
Okay.
Now what?
So what do you think? Let's focus, what letters do we want to focus on?
A and B.
A and B. So shift B. Should we all pick a number to shift B to?
B
So we
against
want to
what?
put
B against the A above it?
B of 1,
So here's times 15.
1 of B on A of 2.
Got it.
What does that do?
That's multiplying. That doubles that. Double it in above the 2, the 4 above the 3, the 6.
No, I don't see what you're seeing.
So let's make sure that we're all sort of A and B.
Yeah.
A doesn't shift, B does. So 2 of A should be above 1 of B. And if we look over, let's go look at 2 of B. And what is an A? Okay, let's shift over. Look at 4 of B. What is an A?
A.
8. So what is this doing? Multiplying by
The B is multiplying by whatever A is. A tells you what you're multiplying by.
It takes our multiplication that we put our B1 on.
Right. That becomes
So
A factor.
that's your A factor.
So
Your B factor you read off of the B.
we take
So 15, 16, 17,
B.
17, right?
right here and we multiply it and look along this line. 2 times 2 is 4. 2 times 4 is 8. So that's where all of these, this is our A, and this is our B.
Okay.
And that's why we have this funky scale.
255.
Can you show me how to multiply 34 times 2?
What do you think?
So 34, you'd have to move the 1 under like 3.4.
So that next one,
Right.
is it by 10? So this is
3.4, and then you'd look over 34 times what?
2?
Times 2?
Yep.
Is 68.
And you
Yeah.
get 6.8 about 68, yeah.
So that's a good question. So why 3.4? If I keep on pulling this out, I want to put my B on 34. So I mean, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it gets back to 1. What does that mean?
That's 10. You could actually do it to the
Oh, that's 10. That's 10. Okay. 10. So I'm guessing that this 2 is 20, and this 3 then 30. So then I go and like 1, 2, 3, 4, 34.
Okay, so what?
I'm not sure which is.
What did we want, what times 34?
2.
2. So we come over here and I get 2.
Oh, I thought you wanted 34 times 64.
There's also
Could we do 64? So, but 64 is all the way over here.
If you could do 6 point.
Yeah, so I don't know what to make.
But we could do 34 times 6.4.
34.
So it seems like one of the things we have to do is be aware of our powers of 10. So if the power of 10 goes off the scale, then we need to take and divide by 10. And does that mean we just forget about it? You have to bring it back in for the answer, for the final conclusion. So you'll get an answer, but it might be off by a power of 10.
34 times 6.4 is 200 and what number is that?
How do you find
About 17. No, 8.
216?
16. Must be 16.
So I put 1 under where?
Because 4 times 4
3.4?
ends in 6, right?
3.4.
So
And the other one on 1, 2, 3,
216?
So it's just to the right of 15, so yeah.
And then that'd be
David's got their slide rules.
6.8.
So can you come show me on this one?
Yeah, but
Can somebody come show me what you did?
64.
It's not the equipment advantage.
What are we multiplying by?
34 by
64.
64.
So 34 by 6.8.
34 by 64.
So can somebody show me on this one?
Danny, go.
I'll even hold it on me for you, so you don't have to do
Go,
it
Danny,
backwards or
go.
upside down.
Go.
So my answer
We're
should
just
be
talking about old
200,
game shows, and this is totally like.
10,
This would be a great game show, yeah.
232.
This is for $10,000, Danny. What is?
There.
Okay, wait.
That's 3.4.
3.4,
So I
okay.
put 1 under the 3.4.
Okay.
And then I look at this, and I want to do 34 times.
No.
64.
No.
Go to 64.
Oh.
64
No,
on the
leave it on
top.
34 and slide over to 64.
Oh.
I thought they said 68, but now they're saying
So
64.
30. So I want to do 64 times that. So I
Or was
go
it 68?
Yeah.
So 150 divided by 7,
And you get
right?
216.
Let's
Kind
go
of.
to
What?
20.
Sorry.
20.
20.
You gotta do your power of 10.
So you wanted to do 150.
So you
So
said
that's
here,
64. I think 34 times 64 is going to be
So-
like 1.
And then
Ah.
oh, it was 200 and change.
That's
2,000.
7 powers of 10. Yeah, I think it might be 21,000.
Dang it.
Um,
I need to get my graphing slide rule out here.
Because you took off 2 powers of 10 to do 6.4 times 3.4. So you gotta add back on.
Right.
7.
Yeah, that makes sense.
Right,
And
and
then
so,
64 on the
and
B
so,
scale.
yeah, and you have to do the.
And
No,
then
no,
up.
2,160.
2, 1, 2, 3.
Yeah.
No, because it has to end in
Those are other
6.
scales.
That's not 24, it's not like 22.
So it's 2,100.
No, this is a completely different scale here.
Yes.
This is
100
8
and 56.
And,
Because that's past the 5.
This is the square root
They were,
scale.
you know, like in terms of.
See, normally you have what you're missing is a thing, like what Jennifer has.
And you get the size of the
Allows
LCD
you to
display.
a rectangle or whatever it is.
So what we did
You
is,
can read them squares.
I just want to make it so that we all, in case you can't see on the giant one, we took our A scale,
So that's all that this is. Ignore it. You're only using these.
and we have our B scale.
Do we use this top part to be more
And the B one is the one that you can
This is
shift.
square roots.
So we shifted our B to the right, and we lined
These are square roots.
one of B up with what?
Square root of 9.
3.4.
3.4.
Square root of
So we made bigger notes. Multiply by 10. And then we come look over here at what? B
Oh,
at
I'm sorry, no, that's 13. That's 13. 1, 2, 3.
Yeah.
Square root of 13.
6.4.
at 6.4. So we note 2. Multiply by 10. And then we look up, and what's above us on A? Let's just do the big ones. So we're between 2 and 3, right? We're really close to 2.
Mm-hmm.
It's like 2.15.
Yeah.
175.
So it's 2.1, we'll say 6-ish, is what I heard a lot of. So we read 2.16-ish on the scale. And then we look at our notes,
Yeah, mine definitely was more than halfway.
and we multiply by 10, multiply by 10, so our answer is what?
2176.
So we
can't tell
multiply
that
it by
from
10
this.
because we went over 10 to the
2.16 times 10 times 10, which is 2,160, and the actual answer
21.
21.76. So that's pretty close. It's pretty close.
Does any of the rest
That
of this help
doesn't
you
seem
be more
close
accurate?
enough to me, yeah.
Bryn, is it? Do you have an output of 2.176 or is it 21.6?
This was 2.16. I was saying that it's close. It's past the 2 mark.
So if it's 2.16 and you multiply it by 100,
Well, we were at the 20. We were past the 20.
You get 216.
21.6. Okay.
21.6.
In general, because
20.
it
That's
has
past
only
20,
the number.
that's 21.
Yeah, because that's that
It
big 2
depends
is
on whether
20.
you read that top scale
Whereas
as
this one
21
here
or
is
as
Ah.
more compressed.
You really think that top scale you read it as
Yes.
20s.
Yeah.
Yeah.
So it's 21.
Because otherwise the multiplication doesn't.
Yeah. So this is 20. So this one's 20. So
I
this
will
one's
assist.
21.
Yes.
Just
This is, yeah.
How much?
Thank you.
So this is a very basic slide. We would like the ones that this one here. 'Cause
Is
it
there
just
any of
says-
the rest of this business help you be more accurate than the other?
All this stuff on top? At 22.
That's a good question. Does any of it help you be more accurate?
Yeah, so like,
Like what's all
What do you
the
want?
K and
Yeah.
Yeah, I think it is.
L?
That does
So-
so much.
What do you think?
20,
So I just want to know what we have a list of all of our letters.
C and D. So like, so like if you put this, yeah, like
So
if you put this up
SKA,
at 22, 2.1, 2.2. And now, anything, so you just, now you can multiply.
We have A, B, C, D. I got that much.
Right?
Okay.
S and K,
K,
K and L. K on the top.
L and T.
I
L
got a
bottom.
C1.
And S and T.
A C or C1.
C, and S.
S.
There's no N. Maybe there's an N.
I'm a C1.
Yeah, you can,
Two C's, a
yeah, you
C
can,
and a
you
C1.
can
Yeah.
line it up this way.
Okay.
Down here, would that be 22?
So another resource to be aware of is that
No,
HP,
that's 1.2.
which is Hewlett Packard.
So what do you do if it's If you want to multiply
has
7 by
a museum of calculators.
So,
This is one of the first calculating devices.
like that.
And they have basic slide rule instructions and all sorts of slide rule history and things like that. So HP reminds us that okay, A and B. A is squares. What do you think B is?
Squares.
The same.
Base?
Sort of, it's square roots.
The A and B scales are the same.
Well, wait. So A is the square of D, and B is the square roots of C.
Crazy.
Oh.
So that means that as you're moving the thing around, A and D both stay stationary, B and C move together.
Mm.
That's sort of cool. Okay, let's see. Does anyone have R?
B is the square of C.
K is the cube and cube root. L is logarithms. Logs. And what do you think S and T are? Looking at this, what do we have?
Sine, cosine.
Sine and cosine and tangent.
Oh,
You don't need cosine.
you're right.
Why don't you need cosine, Paul?
Well, you don't need trig. But actually, back in the day, you needed trig. Yeah, because cosine of cosine is the sine of the complement of the angle. So
Cosine is just
like cosine of 20 is sine of 70.
So complements. And the same thing, so some of them will either have tangent or cotangent. I need to do the same. So if it's S, then it's sine. If it's C, then that wouldn't happen, actually, because C is the other thing. Okay.
Yes, so
And ST is for sines and tangents of small angles. Less than 5.7 degrees. Yeah, so, I mean, there's different ones.
No, she said there's a ST.
No,
No, ST. So, like, this is ST, and it goes between.
Do you have a C1 up there?
So, C1, let's see.
C1 or
Yeah,
C0?
C1 are reciprocals.
Of C.
yes, so here's the 3 you wanted to multiply 2 times 7. You try to multiply 2 times 7. It's no good because the 7's over here. So instead, you multiply.
Okay. So, we're actually at the end, unfortunately, of the time that we have.
I was thinking this was 20. I was thinking this was like up here, how when you said
I'm gonna
20.
just, as you keep on playing, I'm gonna give out some more information. And I'm gonna put together this as a complete lesson plan and put them online, but I wanna try it first. So, what I sent out basically is, starts with the history of the slide rule. And again, when might this actually ever, like, why were they using slide rules? I think that this is something that is going to be important to introduce to your students. Like,
Because they didn't have a calculator?
because they didn't have a calculator.
Here's my other thing.
So when could you use slide rules today?
So if you need them, you just
If you don't have a budget, you can't afford calculators.
There's a hilarious video basically where an engineer is doing all of his homework and then his calculator dies and he runs out of batteries because it's the weekend, so he has to use a slide rule. So, you know, maybe a calculator batteries.
Your class to use slide rules, that way they can't be putting the cell phone talking
So
about.
when I was a nerdy little kid, I used to read science books by Isaac Asimov.
He always has slide rules.
Yeah, and he wrote about about all this great stuff you learn. You know, using a slide rule, you can compute this. Using a slide rule, you can compute that with a few flicks of the wrist. And so I really, really wanted a slide rule, and I asked for a slide rule for my birthday, and I watched the mailman come for weeks and weeks until the slide rule came, and then I had my slide rule. And
did you learn how to use it?
Yeah, I learned how to use it.
Oh yeah. And what was the name of one of Heinlein's best characters?
Asimov.
Slipstick.
Slipstick, yeah.
Highlight.
Well, and in fact, our math team song had Slipstick in it.
Yeah, Slipstick Libby.
Yeah.
So hopefully, I'm sorry. Yeah, sorry.
I get it.
They designed the trajectory for the moonshot using slide rules. Then when you're having trouble on Apollo 13, they did it with slide rules. So they corrected the path, and we did, you know, on the fly, where you really had to do it very, very quickly. And it only took 10 years from the time Kennedy said to get a man on the moon. It'll take us 20 years for the next program now with calculators. So.
And you know, you've all probably heard about the ship, the Endurance. You know, the one that got stuck in Antarctica for 3 years.
Oh yeah, Shackleton.
Yeah, Shackleton's voyage, and when they did the rescue mission to get back to South Georgia, I think, and they were using sort of dead reckoning.
Yeah.
They were saved because there was a table of logarithms on board, which allowed them to do the critical navigation calculations.
Yeah, they were just in a dinghy going from Whale Island to Green Island.
Yeah, so without the logarithms, they would have been toast.
Yeah.
So hopefully, this is a quick introduction, I know, to slide rules. But if you have suggestions, please let me know. And because I think that this is something I was trying to not just sort of throw them at you, but sort of develop a bit more inquiry, you know, so you can check it out if we have more time. Is there any questions before we take off?
I think that when you do your slide rule presentation, you should jazz it up and have some music playing in the background on a turntable, and maybe have the phone ring on one of those old and have somebody taking notes on a typewriter.
So I have to say that this is actually inspired by Paul, because one of the things that he said in defining what a math circle is, this is something that we're always sort of wondering what we are, is that math circles are an important part of creating mathematical cultures, of sharing sort of the legends, the stories, the lore of mathematics. And I realized that this is really, we get so associated with slide rules, and yet I had never played with one. So thank you for playing with slide rules with me today. Yes?
I was just going to make a comment. If anyone watches TED Talks, there's a great one with, the title is 18 Minutes with an Agile Mind, and it's about this physicist who teaches, he went in to teach grade school math, and he's teaching his students how to calculate the speed of sound, and it's really interesting. But there's this portion where he needs to do this really complicated complication, and he just pulls out a slide rule and he goes, here's the answer. And it was kind of neat that he had this great physicist, and he just pulls out a slide rule just to come up with the calculation, to need a calculator.